Hello and welcome back. Today we'll be doing question 2 from the 2017 math paper. This is a question intended for all applicants. There is a unique real number alpha that satisfies the equation alpha cubed plus alpha squared is equal to 1. You are not asked to prove this. Part 1. Show that 0 is less than alpha is less than 1. Part 2. Show that alpha to the 4 is equal to -1 plus alpha squared. Part 3. 4 functions of alpha are given in A to D below. In a similar manner to Part 2, each is equal to a quadratic expression A plus B alpha plus C alpha squared in alpha, where A, B, C are integers. So in part 2, we found A equals -1, B equals 1, and C equals 1. You may assume in each case that the quadratic expression is unique. In each case below, find the quadratic expression in alpha. Part A, alpha to the -1. B, the infinite sum, 1 take away alpha plus alpha squared, take away alpha cubed, etc. C, 1 take away alpha, all to the -1. D, the infinite product, 1 plus alpha squared, 1 plus alpha to the 4, 1 plus alpha to the 8, etc. Pause the video now to have a think, and once you're ready, restart to see if you were correct. Let's get started with part 1. Firstly, we'll take the defining equation and we'll substitute alpha equals 1 and alpha equals 0 separately. In the first case, we get alpha cubed plus alpha squared is equal to 2, which is greater than 1, and in the second case, we get 0, which is less than 1. Since alpha cubed plus alpha squared is continuous, we have that alpha must lie between 0 and 1, as required. Now, we can move on to part 2. Here, we can multiply the original equation by alpha to get alpha to the 4 plus alpha cubed is equal to alpha. And we can also rearrange the original equation for alpha cubed to get alpha cubed is equal to 1 minus alpha squared. Substituting this into the left-hand side equation, we have that alpha to the 4 is equal to alpha squared plus alpha minus 1, as required. Now, we can move on to part 3. For alpha to the -1, we will divide the original equation by alpha to get alpha squared plus alpha is equal to alpha to the -1. Now we'll move on to part B. Firstly, we'll notice that this sum is a geometric series with a common ratio negative alpha. Therefore, S infinity is equal to 1 over 1 plus alpha, and substituting 1 from the definition gives us alpha cubed plus alpha squared over 1 plus alpha, which is equal to alpha squared. Now we'll move on to part C. We can rearrange the original equation for alpha squared, which is 1 take away alpha cubed, and by the difference of two cubes, this is equal to 1 minus alpha, 1 plus alpha squared. Rearranging this gives us that 1 over 1 minus alpha is equal to 1 plus alpha squared over alpha squared. This simplifies to 1 plus 1 over alpha plus 1 over alpha all squared, and expanding and simplifying this gives 2 alpha to the 4 plus 2 alpha cubed plus alpha squared plus 2. This can then be simplified down to alpha squared plus 2 alpha plus 2. Finally, we'll move on to section D. Here, we can say that 1 plus alpha squared, 1 plus alpha to the 4 is equal to 1 plus alpha squared plus alpha cubed plus alpha to the 4, etc. And this is equal to 1 over 1 minus alpha by the summation of a geometric series. From above, this is equal to alpha squared plus 2 alpha plus 2. The transition between the first and second lines works because every single number has a unique representation in binary, meaning that every power of alpha will appear precisely once in the expanded form. This was not expected in the original exam, and you were able to get away with it by simply expanding 1 plus alpha, and then expanding 1 plus alpha squared, then expanding 1 plus alpha squared, 1 plus alpha to the 4, and noticing the pattern. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching, and goodbye.